So here it is, your headfirst guide into single image super resolution using deep neural network. So to begin with, it makes sense that we understand from the very scratch and begin with what is single image, what is super resolution, and then what is neural network, and when does it become deep and when it is shallow. So super resolution refers to the process of converting a low resolution image into its corresponding high resolution image. On the first picture, I have on the above the low resolution images and that we perform super resolution on. So these are the inputs and these are low resolution images. We perform super resolution, and as the output we get the images that are below them, and those clearly are much more focused and sharper because they have more number of pixels, and they are corresponding high resolution images that we obtain by performing super resolution. So you can also think of it as incrementing the number of pixels in an image. Oftentimes you have your old videos from your childhood which are not in good quality. Let's say they are in 360p, and now you want to somehow convert it into 480p so that you can enjoy it with better clarity, but those pixels are simply not there. When you were recording it, they were not captured, the information is not there, but we want to be able to somehow get those information that we didn't capture in the first place. How do we do that? Is that even possible? It is, and how we do that is what super resolution is all about. Now that we understand what super resolution is, let's take a step forward and try to understand what single image super resolution is. Single image in what sense? Well, when we have a single image and that is a low resolution image, and we use that single image to perform super resolution and obtain a corresponding high resolution, that is single image super resolution. Alternatively, what happens is I click the photo, or I have the images that were captured in a continuous burst of shots with a very high shutter speed and in a very small interval of time. So I use all those set of images and perform super resolution and use all the images to come up with a high resolution single image, but that used all the set of images made before 545, whatever it may be. It used all those multiple images, performed super resolution, and gave output as a single image. Basically, super resolution refers to enhancing the resolution of image from low resolution to high resolution. Super resolution applications include face detection in surveillance, where we can perform super resolution on the CCTV footages to better be able to detect the face. In medical, we can apply super resolution on MRI scans to get better quality scans that are more clear. In media, we can transfer low resolution content from the transmitting end so that we have faster transmission, and since we are transmitting low resolution, that is basically low data, it will be faster and more efficient, and on the receiver end we can perform super resolution, thus not compromising with the quality. Now let's move on to the methods and techniques that are used for performing image super resolution. The basic methods involve pre-upscaling super resolution and post-upscaling super resolution. And as we move towards advanced methods, we have residual networks, recursive networks, progressive reconstruction networks, attention-based networks, and generative models. Later on in this video, I'll be talking about residual networks and attention-based networks, but feel free to explore all the methods and techniques. And as we move forward, it is essential that we understand, for the task of performing image super resolution, why do we need neural networks? According to data processing inequality, you cannot add data to something that's not already there, irrespective of whatever way you process it. So, do you think this statement is completely true? If you don't think so, let's make this a discussion in the comments section. because we do have image processing as an alternative to do or perform the image super resolution. But however, we are opting for neural networks and not image processing. So let's make that a discussion in the comments and move forward. Neural network is nothing but a specific type of machine learning model. The types of neural networks that we have is artificial neural network, then we have convolutional neural network, and also the recurrent neural network. We are going to use convolutional neural networks for performing image super resolution. Let's take a quick peek into its history. In 1965, first feed-forward multi-layered neural network was discovered, but it was only after the backpropagation algorithm was discovered that the feed-forward multi-layered neural network was of some use. In 1989, first convolutional neural network was discovered and it was used for detecting handwritten digits. In 1998, LeNet-5 was a popular algorithm that attained astonishing accuracy in detecting handwritten digits. Well, convolutional neural network was discovered in 1989, and from then it stayed in sleep mode for the next 2 decades. Well, basically, it was because there were some issues that seemed impossible to be solved for 2 decades, and one of those was the gradient descent problem. However, in 2010 or 2006, things began to change, and the problem that seemed impossible was solved, and convolutional neural network exploded with researchers doing various researches in various domains. And then came image super resolution, where convolutional neural networks came to be as a perfect fit for performing the task. As the convolutional neural networks grew deeper, residual learning framework was introduced to better efficiently manage the computations. So here we have a list of neural network models that were used and considered best by their standards at that time. And we observed that by 2010, the neural networks were just shallow. And only in 2012, deep neural networks were appearing, and that too with just 8 neural networks. However, from 2014 to 2015, we see that something major changed, because before 2014, maximum number of neural network layers were 20, but in 2015 now we have 150 number of layers. And how is that made possible? What changed? Well, researchers discovered residual learning, and residual learning fixed the gradient descent problem. What was the problem actually? Let's discuss that. The algorithm for computing gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation. The process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. Basically, it is a way to converge towards some local minimum of a cost function, basically a valley in graph. So as the layers in the neural network grew deeper, somewhere around 30 layers, what we observed that the gradient was either getting to zero or sometimes getting to infinity, and we termed those as vanishing gradient problem and exploding gradient problems respectively, and those caused all sorts of problems. However, thanks to residual networks introduced in 2015, we were able to solve those problems, and that enabled us to go deeper. What we have in residual networks is skip connections. The advantage of adding this type of skip connection is that if any layer hurt the performance of architecture, then it will be skipped by regularization. And this simple concept solves the vanishing exploding gradient problem. Now, by this time, image super resolution had become a very computationally expensive task, and researchers had to figure out some way to make it less computational. and thus came the attentional mechanism. Well, we have in attention mechanism spatial attention and channel attention. What we are doing in attention mechanism is giving selective attention to different regions in an image, and that gives us better results, and which is less computational. So while our neural network models are training themselves, they are not paying equal attention to every part of the image. They are paying more attention to the parts of the image that are more meaningful and learnable, and less attention to which seems like waste, and that way they are able to better learn and use their resources more efficiently and consume less computational resources. So what happens is the high resolution data in the image, those will be the edges, are more important data and are paid more attention while the model is training itself, and low resolution image or the low resolution portion of the image where there is no edge, no texture, just the filled color, what happens is the model does not pay much attention to it because there is no meaningful learnable extraction from it. Because in high resolution, what we want to do is we want to make the edges sharp. We know that the color is filled, we have nothing to do there. We just want to be able to better identify the edges and make them sharp. The field is exploding with researches, and then some people came and suggested that we should implement attention in attention network, and that would be like there is an attention module that is paying attention to, that is deciding how much attention to be paid on what portions of the image. Now there will be another attention module that will pay attention to this attention module and make sure that it functions properly. So yes, the field is going crazy. Everyone is trying something new, and whatever works is being published. However, these were the references that I used for the preparation of this presentation. Feel free to check them out and learn more. And try to go crazy in this research field yourself as well. Try ISO based attention mechanism, try tonal range based super resolution, try anything that hits your mind, and try to come up with some results that outperform the present models. Best of luck with your future endeavors in this field, and thank you for watching this video.